when little Sewer said, "Bust a cap in that mother gangsta, what thank bust him." What he meant to say was opening up a capacitor in your mama's old dank workshop. Now, I don't recommend opening up a capacitor because there's acid in there, and not the fun kind of acid. So I did what any reasonable man would do, and that's I opened up a capacitor. And here's what's inside. So this is what a capacitor looks like, and I'm not going to show you how I opened one of them up because I don't want you to do it, and it also involved a lot of, brute force, and I got just a kind of a pile that I got out of it. So out of one of these came all this stuff. So let's just see what it is. Well, here we have an end cap type of thing, which holds these two prongs in there, the little metal prongs, and these are here, and you can see that at the end they have a little nubbin there, and the nubbin is so it stays in. This, if the capacitor is made poorly, can actually fly off and catch you in the eye if it explodes. So this is why, let me just make sure you can focus there. This is why there's this little cross on the top. This cross, this indentation can actually expand, and then it will release gas if it wants to explode, so the cap doesn't bust off. That's what they mean with pop a cap. That's what pops. And that's not what they mean. I know actual culture. So these are little prongs. And one of them is attached to the conductor and the other is attached to the ground. There's a little plastic protector thing around it. And this, there's more of the plastic. This is the main attraction. So here, it's been a while since I opened it up, 2 days, but it used to be much wetter with all the acid on it. And you can see here, this is quite shiny, and this is aluminum foil basically. I'm not sure if it's aluminum or aluminium, if you want to call it that. Not sure if it is that, but it is quite brittle. You could just kind of tear it, and it's little pieces of metal. Right here you can see where it connects to one of these prongs. Just get that. It was soldered onto one of these. And in between, you can see when it's still rolled up, because it was rolled up inside of it. You can see there's, in between the two plates of aluminium, there was this piece of paper which was wetted with the acid that I just mentioned. So that piece of paper is in between, so that does not conduct electricity, so there is an insulator between the two conducting materials. And that is what a capacitor is. There's just two plates of metal, usually aluminium foil, and some non-conducting material inside it. And there's acid in there for reasons, for making it even less conductive and also being able to charge it. I'm not quite sure about all that, but that's just what's inside, and it makes a mess, you can see. It also made my fingers look like this. Ew, all the acid made it like that. Don't open up capacitors because they'll make your hands look like mine. Ooh. So you can push electrons onto these little plates here, and you can only push electrons on the outer edges of any conductive material, so you need a lot of surface. Now, what is a capacitor going to do when it's full, when there's so many electrons that you can't really push any more electrons on it? It's gonna blow up? No, it doesn't. It doesn't blow up. It starts pushing back. All the electrons, they start pushing back against the voltage. And you can literally think of the electrons as pushing against the voltage. because that's kind of what they're doing. They don't want anything to do with more electrons. It's full, and they're going to start pushing away all these new electrons. So what it's basically doing is making resistance. So a capacitor becomes kind of like a resistor when it's full, and that's handy dandy stuff, especially when we're going to put it in an AC circuit. Now, you wouldn't put it in an AC circuit, would you? That'd be crazy. We do it all the time. AC circuits and capacitors are kind of like two peas in one PP, or a pod. And where am I going with this again? Script, please tell me. Look at this graph. Look at this graph! No, not that graph. This graph. You've seen this graph. It's a sine wave, and this is the 0 line here. And all these electrons are moving one way. On the top side, they are going that way. And when the sign is on the negative, all the electrons move this way. So they go back and forth. We've talked about this in the video called AC/DC, not the band. So if we're pushing electrons on a capacitor for a very long time, well, like I said, it becomes a resistor. And eventually, this whole part, it's pushing electrons on it in that direction. And then here, it starts pushing on the other side. So, you can fill up the other side of the capacitor. So it's going to resist. But what if I make a higher frequency? Let me just draw another graph. So this is a low frequency, and this is a higher frequency, also much less nicely drawn, but there's this weird kink in the cardboard. So what happens here? Well, it's doing the same thing, but it's doing the pushing and the pulling a little bit differently. It's pushing electrons here, but before the capacitor can be full, it's already pushing on the other side. So the capacitor, remember, really reaches a point where it starts resisting the current. So it doesn't give as much resistance. So actually we have a frequency-dependent resistor? Yeah, it's a resistor that resists more when there's a low frequency and less when there's a high frequency. Capacitors don't like low frequencies, and they don't really mind high frequencies because of this pushing of electrons. So in theory and in practice, we have a frequency-dependent resistor, which is dope because, look, here's our friend, the voltage splitter again, but he's evolved because now he has a capacitor in here and a resistor. The resistor is the same thing, but there's also a capacitor now. And this capacitor, apparently, it reacts to certain frequencies. So a lower frequency will give this a high resistance. So all my voltage is going to be on this capacitor because it's a high resistance. And at low frequencies, this is a battery, it should be AC actually, just don't really mind that. On low frequencies, it's gonna get a high resistance. On a high frequency, it's not gonna mind, so the resistance is all in there, so all the voltage is going to go over R, so nothing's going to really go on this parallel part of the circuit here. That's very useful. It is a frequency-dependent voltage splitter, which also has a different name, and we'll go into that in the next video. It's called a filter. I can just tell you that already. It's called a filter. We're going to talk about filters in the next video. That's where it becomes fun. That's where it becomes very audio. If you're about light, then I can't tell you anything. I think audio is more fun. And, as always,
while I am a licensed physics teacher, this does not make me an expert on the subject. I'm wrong sometimes. Sometimes I know I am, but simplify my explanation at the expense of being completely correct. Sometimes I actually don't know. In either case, I've got a pretty good grasp on the laws of nature and how things work. For the purposes of these videos, the exact correct descriptions of phenomena is not important. I'm trying to give students a new way to look at this world with a technical and logical view. Please feel free to contact me to discuss any of the subject matter within the video.
have a good one.